Good afternoon. I'm Kenichi Rinoye from the University of Tokyo, and I'm going to chair this session. This session is titled Japanese R&D on GX and DX in Aviation. And first of all, this session was originally proposed by our ICAS president, Professor Dimitri Mavris, last year, and he contacted JAXA to organize this kind of session which explains the Japanese activities. And his intention is, he says that this is a Japanese showcase. And next time, next Congress, probably the other country will organize this kind of session. Okay, so this is our ICA's first time to organize this showcase session. And today we have 4 papers, and the first one is an overview of Japanese activities, and second one is mainly focusing on the sustainability, I mean the hydrogen aircraft, and third one is focusing on the digital technology, and fourth one is also the sustainability, I mean the hybrid electric propulsion. So we have 4 papers. Now, the first paper is titled Overview of Japanese R&D Activities on Green Transformation and Digital Transformation in Aviation. And the paper is presented by Shigeya Watanabe, and he is a Deputy Director General of the Aviation Technology Directorate at JAXA since 2022. And his research interests include advanced aerodynamic measurement technologies, aerodynamic drag reduction technique, EFD, CFD integration, and aerospace vehicle design. Okay, so please, Mr. Watanabe, start your presentation.
Thank you very much for your kind introduction, Professor Rinoye. So good afternoon, everyone. I am Shigeya Watanabe from Aviation Technology Directorate of Japan Aerospace Exploration Agency, JAXA in short. So first of all, I'd like to thank Professor Dimitri Mavris for offering this special session dedicated to Japanese activities in aerospace aviation sector. So also, it is my great pleasure to be here to be able to present you overview of the Japanese R&D activities on green transformation GX and digital transformation DX in aviation. Okay, in my presentation, firstly, I'd like to talk about briefly global trends for this green transformation GX and digital transformation DX. So green transformation GX is recently well used in Japan. The meaning is pretty similar to sustainable aviation, which is a very common term in aviation world. But on the other hand, DX, digital transformation, is a well-known term in the world. The next, I'd like to introduce framework of the aviation DX and DX in Japan. Then I'd like to introduce some featured R&D activities in National R&D Agency, that is JAXA, aircraft industry, and academia. Okay, first I'd like to talk about global trends for GX and DX as background. Thinking about circumstances of the global aviation, civil aviation market is expected to continue expanding after the severe shrink due to COVID-19 pandemic. In this trend, Asia-Pacific region is particularly a promising region that will drive global aircraft demand. In addition to these situations, the global aircraft industry is coping with new challenges such as decarbonization, that is GX, DX, and supply chain resilience. METI, Ministry of Economy, Trade, and Industry of Japan is strongly emphasizing these new movements in global across sector as shown in this figure. Top two items in this movement is decarbonization, that is GX, and digitalization, that means DX, indicating that the top priority is put on GX and DX in METI's strategy for Japanese aviation industry. Also, I'd like to emphasize that the strategy of METI put a strong emphasis on growth of Japanese aviation industry through international collaborations. Thinking about the background of GX, so important topic is that global target of net zero carbon emission by 2050. So ICAO Assembly adopted this aspirational goal 2 years ago. Based on this situation, GX sustainable aviation has become the worldwide challenge in aviation sector. As you know, since only one solution is not enough to achieve this goal, various solutions such as SAF and new technologies like electrification and hydrogen, as well as successive improvement of conventional technologies should be pursued to achieve this goal. So in terms of DX, the complexity of modern aircraft causes massive rework in design phase. As a result, the period of development is getting lower, as shown in the left side figure, and the development cost rises drastically accordingly. So to solve these challenges, utilization MBSE, model-based systems engineering, and multidisciplinary analysis will be crucial. Also, the process of type certificate is prolonged mainly due to the usage of advanced materials such as composite materials, as shown in the right-hand side figure. So this means that also a development method for CBS, certification binary analysis, is very important. Okay, let me talk about the framework for aviation GX and DX in Japan. From the 3 points of view, overall framework and framework for standardization and consortium as ecosystem. Japan's overall framework covers everything from government, national R&D institution, academia, and company, as shown in these figures. So gray boxes shows government-related organizations, which mainly consists of 4 ministries in charge of science and technology, industry, transport, and defense. So one of the challenges to make this overall framework active is to strengthen the collaboration with of 4 ministries to facilitate the R&Ds in Japanese industry and other sectors. JAXA is Japan Aerospace Agency is a unique R&D agency specialized for aerospace technology in Japan. So it has a role to as a hub to connect all partners in this framework, government, organization, academia, the company, and to facilitate the collaboration among these partners. A second framework is Public-Private Council for New Aeronautical Technology towards CO2 emissions. So actually, the chairman of this council is Professor Inoue. This council is aiming to formulate safety international standards for new technologies and to contribute to decarbonization in the global aviation sectors. The feature of this council is that both public and private sectors collaborate mutually with each other under the management by two ministries in charge of transport and industry. These are EMIRIT and METI. There are three working groups under this council: electrification, hydrogen, and weight saving and efficiency working groups. As well as domestic collaboration under the council, we have collaborations with international standardization organizations, foreign aviation authorities, and ICAO. For example, some members of this council, such as JAXA and several aviation industry, participated in E40 committee of SAE on electrification of aircraft. So in future, we'd like to propose standard drafts to SAE on electrification of aircraft. The third framework is a consortium as an ecosystem for open innovation in aviation activities. The one with the consortium in charge of GX is Electrification Challenge for Aircraft Consortium called ECLAIR. This consortium was established 6 years ago, led by JAXA. Now it has 148 members from the various sectors of expertise. At the beginning of this consortium, it created the future vision of electrification of aircraft, and then it made and shared the technological roadmap towards this vision. Now, under this consortium, many partners are doing the many kinds of collaborations along the technology roadmap. The second consortium in terms of DX is ChainX, which was established 2 years ago, led by JAXA, with the support by METI, JADC, JAI, and so forth. Now it has almost 50 members. The objective of this ChainX consortium is to expand the scale of Japanese aviation industry and strengthen international competitiveness by DX. Under this, to fulfill the objectives, the mission of this consortium is to create innovation of development, production, and services in aviation industry by promoting DX throughout aircraft life cycle. Okay, let me move to the featured R&D in National R&D Agency, JAXA. 3 years ago, JAXA Aviation developed vision of future aviation under the pandemic of COVID-19. The slogan of this vision is environment, people-friendly, sustainable society utilizing aviation. Like us, okay. The keyword of this vision is sustainability, like sustainable aviation. This vision consists of 3 categories: transport, aviation industry, and aviation integration and industry. So GX is the first priority in this vision, while the DX is also strongly emphasized in this vision. Okay, next I'd like to introduce two large projects in terms of GX in JAXA. First one is the ongoing project on environmentally compatible core engine technology research to reduce CO2 emissions of conventional turbofan engines. The goal, detail of this project was already presented in this morning in this Congress. The goal of this development, of this project is to develop key technologies for environmentally compatible core engine. So Japanese aero engine industries have not so big share at the high temperature and high pressure components in the international aero engine developments. So we aim to have a higher share based on the new technologies which will be acquired in this project. We are conducting dual developments in ultra-low NOx lean premixed combustor and high pressure, high efficiency turbine. So we are conducting this project in close collaboration with industry, such as Kawasaki Heavy Industry, KHI, and IHI. The second R&D topic is in terms of GX in JAXA is on hybrid electric engine to reduce CO2 emission for future aircraft. The goal of this project is to develop technology for electric aircraft and contribute to expansion of Japanese aviation industry. We are developing and demonstrating the feasibility of JAXA's original concept for hybrid electric engine as shown in the right-hand side figure. This concept called Watt Wake Adaptive Structure is a kind of BLI, boundary layer ingestion concept, with twin electric fan mounted on the rear body and configured shape rear body as shown in this figure. So electric generator is installed. The electric generator installed in the electric turbofan engine on the low pressure axis then generates electricity for electric motors to propel electric fans. So we aim for first technology realization to be possibly implemented to next generation narrow body type aircraft in 2030s. So we chose the size of narrow body is because more than half of the CO2 emission is caused by the narrow body size aircraft, meaning that the effect of the CO2 emission reduction is very important. So also we have a concept with low risk, which is partial turboelectric type without battery and hydrogen, which needs a long-term development realized in real aircraft. So in this project also, we also collaborate with domestic industry partners closely, such as IHI. So, and detail of this hybrid electric propulsion system will be presented by IHI in this session. So main topic in terms of DX is on aircraft design certification, production, and process integration. This project was strongly supported by MEXT through NEDO, Next Generation industrial new energy and industrial development organization, technology development organization. The goal of this project is to develop and demonstrate the aircraft design, production, certification processes by utilizing digital technologies. This project was being conducted in collaboration with aviation industry, as shown here. This project covers design DX, certification DX, and projection DX, as shown in these figures. The key technologies for each area is MBSE, model-based systems engineering, and certification by analysis, CBA, and digital thread, respectively. So as a basic system of this project, we are developing DX platform to share various kinds of data and information among partners of this project. The detail of this project will be presented by MHI in this session. Next, I'd like to talk about the two featured R&D topics in aircraft industry and academia. First topic is being done by aviation industry is hydrogen aircraft core technologies. KHI is undergoing this project with support by NEDO from 2021. The key technology covers hydrogen combustor, hydrogen supply system, and liquefied hydrogen tank, as well as conceptual design of overall vehicle. JAXA is supporting with cryogenic pump technology and liquid hydrogen test facilities. This detail of this activity will be presented by KHI in this session. The second topic by aviation industry in terms of GX is hydrogen fuel cell electric propulsion system technology developments. So IHI Aerospace started this project this year and will continue it for 6 years. So as shown in this diagram of the system configuration designed for 40 passengers aircraft consists of liquid hydrogen tank, heat exchanger, and hydrogen fuel cell, and battery, and electric motor, as well as power electronics like inverters, as shown here. Okay, finally, I'd like to briefly mention about R&D activities in academia. Some universities have industry-funded courses for joint research between industry and university. Recently, GX won major collaboration themes, which includes conceptual design of hydrogen aircraft, as shown in this figure. Also, some universities have collaborations with industry in government-funded projects on GX, such as ammonia combustion hybrid air engine system. On the other hand, Japan Society for Aeronautical and Space Sciences, JSAS, has a role to connect academia, research institution, company, and government for fostering aviation R&Ds. So summarizing my presentation, I overviewed Japan's aviation R&D activities for the purpose of GX and DX. In aviation sector of Japan, both GX and DX are being highly focused in accordance with Japanese government policies, such as carbon neutral by 2050. We are utilizing ecosystems for GX and DX in open innovation manner, including international partners for effective R&D with high impact outcome. Thank you very much for your kind attention.
Thank you very much for your presentation. Okay, so the question time, if you have questions or comments, please. Yes, please.
Hello, Martin Hanford from Saab. Thank you very much for a great introduction to the work of JAXA. General question, as you say, the Asia-Pacific area is going to grow. That's where we're going to see the growth in the aviation market. What is the JAXA, or I would say maybe Japan's or JAXA's vision of Japan's role in that? In that sort of where the expansion is going to be.
So your question about our direction of DX and GX?
Sorry?
Yeah. Would you repeat your question again? Sorry.
I was looking with the sort of expansion going to be in the Asia-Pacific region for the aviation industry. What's the vision of the Japan's role in that, or JAXA's vision of where Japan should be in that sort of expansion?
Okay, thank you very much for your questions. So Japanese industry and also JAXA has a very nice technology for which it will be used for future aircraft. And so first we developed such kind of technology mostly inside Japan, and then we collaborate with outside partners like international OEM and also outside research institutes or something like that to be installed, implemented to the future aircraft. So the Japanese government helping Japanese industry and JAXA to facilitate such kind of activity for the future development of aircraft.
Thank you very much.
Does this answer your question?
Yes, thank you very much.
Thank you very much.
Yes, please.
Flavio Silvestri, TU Berlin. Thanks for the talk. My question is regarding the possibility for international collaboration. So I don't know if your program permits to do collaboration with other countries. For example, in Germany, there is a LUFOS, a very similar program in green aviation, and then each part would be funded by its own program. Is there this kind of mechanism in your funding program? Thanks.
Okay, thank you very much for your questions. So we can collaborate with international partners. So in-kind collaboration is very easy. So each part has a budget and people with each other, and it is very easy collaborations. We have a lot of collaborations. For JAXA, we have very strong collaboration with international research organizations, for example, DLR in Germany and NASA in US. So in such case, so both fund and also budget comes from each government or something like that. But so there is another mechanism, so such as EU has some mechanisms to fund such kind of international collaborations. It is one possibility, I think. Also, Japanese government is thinking that the collaboration with foreign partners is very important, so they try to have a fund for that collaboration. Okay. Thank you very much.
Okay. Is there any other question? One more. So I have one question regarding to the previous question. You mentioned about the collaboration with NASA or the DLR. Could you introduce some activities with DLR or NASA? Okay, so so yesterday, so there was a special session for IFR and ICAS collaboration. So IFR stands for International Forum for Aviation and Research. So it consists of international public research organizations from all over the world, from 27 countries now. So in the frameworks, we have a very easy collaboration with such kinds of public organizations like DLR
ONERA, NASA, and other research institutes. So, for example, so we have some collaboration regarding that research topic with DLR is composite material and also supersonic transport and any other things. So we have a lot of topic for collaborating. So we also have NASA about supersonic transport and also UTM type collaborations. We have a lot of collaboration topic now.
Okay, thank you very much. All right, so thank you very much for your presentation. Let's move to second presentation. Thank you. Our next one is titled Development of Core Technologies for Hydrogen Aircraft. And the paper is presented by Dr. Masahide Kazari. He is a group manager, Hydrogen Aircraft Core Technology Research Project Group, Kawasaki Heavy Industries. And he has been engaging in many researches relating to the various engine technologies, such as pre-cooler for spaceplane engine, or the turbine cooling technology for gas turbine, or the motorcycle supercharger, like that. Okay, so Dr. Kazari, please.
Thank you very much for kindly introduce Professor Illinois. I am very grateful to introduce the development of core technologies for hydrogen aircraft here today. This is today's presentation agenda. First, I would like to introduce overall hydrogen activity in Kawasaki heavy industry. And so, next, I would like to introduce development of core technologies for hydrogen aircraft. Before getting in the main topic, I would like a brief introduction of Kawasaki heavy industry, which called KHI. We have over 100 years experiment to provide the many kind of products. I think motorcycle is most popular all over the world. So next, I would like to introduce vision for CO2-free hydrogen supply chain in KHI. Hydrogen can produce many ways. With, for example, with abundant new renewable energy, like solar power and or wind power with electricity. Produce hydrogen liquefied for efficiency transport. Liquefied hydrogen loaded in electric carrier ship and transported to the usage countries. It can use many various ways. For example, process use of industry and fuel cell vehicle, and so power generation fuel. KHI now concentrate to develop many kind of hydrogen-related technology. And next slide, I would like to introduce some kind of the hydrogen-related technology development. This slide shows the world's first electric carrier ship, Suiso Frontier. Suiso means hydrogen in Japanese. This ship has one electric tank. This tank uses a double shell vacuum insulation system, which allow insulate without external energy, like a thermos. This ship demonstration already started 2022, and we successfully to transport LH2 from Australia to Japan in 2022, end of 2022. This photo shows the liquefied hydrogen loading terminal, High Touch Kobe, in Kobe Airport Island. You can see the Swiss Frontier dock in the base. Loading arm system connect to the LH2 tank of ship to unload it LH2 to the terminal tank. This slide shows the power generation system for hydrogen gas turbine. Hydrogen gas turbine unit set in this package box. In hydrogen gas turbine unit, we develop the hydrogen combustor, and other parts is almost same as a conventional gas turbine. This power plant already started demonstration before 6 years ago, and we continue to the demonstration operation to improve this system. Before I mentioned to the hydrogen-related products, we will further development of hydrogen-related product and business. And hydrogen aircraft car technology development is also started. Next, I would like to introduce the decarbonization of civil aviation. I think you all know very well. Each country has set a target for reducing CO2 emission to prevent global warming. All industry sectors need to make efforts to reduce CO2 emission. In the civil aviation industry, ICAO adopt a collective long-term global aspiration goal of net zero carbon emission from aviation by 2015. Expectations are rising for new technology such as SAF, hydrogen, and water that will reduce CO2 emission. This page shows a movement towards carbon neutrality for aviation. Airbus announced a research and development plan for hydrogen aircraft, aiming to market launch in 2035. Boeing opened a research and technology center in Japan in 2022 to conduct research on SAF and electric and hydrogen propulsion. Rolls-Royce already demonstrated to the hydrogen turboprop engine. Next, I would like to introduce development of core technology for hydrogen aircraft. This slide shows the CO2 emission by aircraft size. Vertical axis indicates the range of aircraft, and vertical axis indicates the seat number of seats, aircraft size. And dark blue area indicate the high CO2 emission rate. Light blue area indicates the low CO2 emission area. And you can see medium-sized aircraft emitted the CO2 67%. And range of less than 27 30,000 kilometers account for the 39% of total CO2 emission of all aircraft. This size of typical aircraft of this type is Airbus 320 or Boeing 737. And we set the target to apply core technology of hydrogen aircraft to apply this range, because if this range of aircraft will be hydrogen aircraft, it's a very significant impact to reduce the CO2 from the emission of the CO2 emission of the aircraft. Next, several hydrogen aircraft configurations are under consideration around the world. KHI selected hydrogen aircraft as target for technology development because this type is simple system and lightweight, and the reliability of existing aircraft can be inherited. This slide shows the hydrogen property versus jet fuel. You can see in view of energy per unit volume, hydrogen, liquefied hydrogen is 1/4 times of jet fuel, and gas hydrogen is 1/8 times of jet fuel. And in view of the advanced flame temperature, hydrogen flame temperature is 160 Kelvin higher than jet fuel. So according to these properties, use of hydrogen as aviation fuel, LH2 is needed for volumetric efficiency, and LH2 tank require high performance thermal insulation and suppress NOx promotion from high temperature flame. So KHI now undergoing R&D core technology of hydrogen aircraft such as combustor, supply system, liquefied hydrogen tank with aircraft conceptual design supported by NADO. This page shows the schedule of this project. This project started in 2021 and continued to 10 years. We already finished the concept design phase, and now we conducted the component development. And final phase, we plan to conduct integrated system ground test. We promoting development in collaboration with research institutes such as JAXA and companies which have various specialized technology. For example, Sumitomo Precision, Nixo, and KITS. And the role of each organization is written here. This page shows the liquefied hydrogen tank development policy. This graph shows the storage period versus tank weight. Ground tank and carrier ship tank require a long storage period, and these tanks use vacuum insulation to hold the high performance insulation. On the other hand, rocket tank not use so required not so long storage period, and the tank can use the single cell type type insulation system, and that tank achieved a lightweight. So hydrogen aircraft LH2 tank that require longer storage time than rocket tank, and weight reduction from the ground tank or carrier ship tank. This page shows a liquefied hydrogen tank development status. We is currently developing metal tank and composite tank by using KHI development experience of aircraft structure and H2 tank for carrier ship and ground facility. This illustration shows a concept design of double shell vacuum insulation. And this hot shows a trial aluminum tank and trial composite tank. Now we conducted the manufacturing test and also material test. This slide shows a hydrogen combustor development. Hydrogen aviation engine combustor is under developing by using hydrogen low NOx combustion technology for industrial gas turbine, which called the micromix technology. Stable combustion and low NOx emission over wide operating range are required for aero engine. Micromix technology uses many small frames to prevent the following cause of NOx emission. One first is a hot spot in the frame. A second is long residence time in high temperature gas. You can see Micromix technology uses high speed airflow and hydrogen injection. It can immediately mixing and make the small flame. This technology basically developed in FH Aachen University in Germany. We collaborate the FH Aachen University to improve this micromix technology. This page shows the development status. High pressure combustion tests were conducted at Aachen University in 2022 and will conduct this year. Improvement the micromix burner are being carried out through the element test and numerical combustion test analysis. And this movie shows a combustion test image of high pressure test. Unfortunately, hydrogen flame invisible, but you can see the some parts red hot. And this slide shows a flame visualization test with high-speed camera is conducted in low-pressure combustion test research flame stability. We set the optical window to capture the hydrogen flame by high-speed camera. This case is a stable frame of micromix, and this case shows an unstable frame of micromix. Unstable frame is cause of oscillation combustion, and we will conduct many kind of preliminary tests to improve the stable combustion. So this page shows a liquefied hydrogen pump development. This illustration shows a booster pump developed by Nixo company. This hydrogen supply system uses two kinds of pump. One is a booster pump, and another is the engine pump. Booster pump set between the hydrogen tank and the engine pump. This hot shows the LH pump test facility in JAX, and now we conducted performance test with LN2, and LH2 are currently being conducted. So this page shows integrated ground test plan. We plan to conduct integrated demonstration ground test of complete hydrogen system from liquefied hydrogen tank to hydrogen engine in 2029 to 2030. We will use aero hydrogen engine. This engine developed in Kazari. So first test operation of this engine with hydrogen fuel will conduct in this year at JAXA nozzle test facility. So this page shows a hydrogen aircraft concept study. Hydrogen aircraft concept is currently being considered, and this illustration shows tank position is front and rear, and seat is between these tanks. So this table shows another configuration. This case is we set the LH tank side and rear, and this case shows a case of blended wing body aircraft. And also we conducted wind tunnel test to measure the aerodynamics and to improve the performance. So we use a summary of this presentation. So reduction CO2 emission in all industry is an urgent task to prevent global warming. There is a growing demand to reduce CO2 emission from civil aviation, and Kazari heavy industry aim to contribute to the decarbonization of aircraft through the development of core hydrogen aircraft technology. And this work is supported by the New Energy and Industrial Technology Development Organization. Thank you so much for your attention.
Thank you very much. Okay, so question time. Yes, please.
Thank you for the presentation. You mentioned the development of two hydrogen tanks, one in metal, one in composite. But from what I've read in literature, it's quite tricky to produce a tank with composite because of the properties of hydrogen. What lesson did you learn with that test tank?
So now we conduct the development parallel, and metal tank and composite type. And after we will choose which is better for the hydrogen aircraft. But in this phase, we must to develop the many kind of the manufacturing technology and also the material improvement to adapt the tank for the hydrogen aircraft. Okay.
So other question? Yes.
Hi, Eduardo Lobão from ATI, UK. I wonder if you guys already have a target or working with some numbers on gravimetric efficiency of those tanks?
Now we consider about the target of the GI index, and I think approximately it's 50% final target, 50%.
And any other question? So I have one question. Okay, sorry. Please.
Yes, I have another one, but I think that from the fact that you're having test benches and that you're developing so many core technologies, I was wondering if you were aiming to look into synergies between those technology, like using the heat from hydrogen or the cold from hydrogen to cool down some of your components and this kind of things.
Could I confirm your question? You mean we conducted many kind of hydrogen-related technology development and synergy?
Synergies between those
Okay,
technologies.
okay, I understand. Yes, we already information exchange to each other team to develop the hydrogen-related product. So I mentioned it before, and hydrogen combustor, we have many experiments to develop the hydrogen combustion technology for industrial gas turbine. That industrial gas turbine combustion technology applied to the air engine. And so the tank technology is almost same. Ship tank technology applied to the aircraft tank technology. Okay.
Yes, please.
I have a question about the fuel cell, because you didn't mention fuel cell in your presentation. So I imagine that you didn't investigate the solution for hydrogen usage. Is it the case or not?
So I understand many institutes and many universities to conduct research of the fuel cell type hydrogen aircraft. But in this time, we think that the category size of different. I think so. And the engine type is a benefit to the more big size aircraft. I think.
Okay, thank you.
Thank you.
Yes.
Martin Behrens, Technical University Vienna. You've showed this transport ship. What is the application? Is it only a demonstrator, or has it already a commercial purpose to transport liquid hydrogen from one point to another?
That ship is purpose is only demonstration, but we now conducted the scale up the ship for commercial. I think it's will be complete the big size its carrier ships will be 2030. So after that commercial size big size carrier ship. It have to conduct the many kind of tests, but the size is almost same to commercial case, I think.
Thank you.
Oh, okay, so final question.
Thank you for your presentation. I want to know why it can, on the page 29, and why it can reduce drag when the tanks are placed at the front or rear of the fuselage.
So I cannot preview. So you mentioned the tank layout in the fuselage.
The tanks are inner of the fuselage. So which kind of drag?
Drag?
Reduce?
I think so. I understand. So, and front and rear type is most benefit to reduce tank. And side tank configuration is a little bit increases the drag. So, and now we conducted the wind tunnel test to research and to take the more information to improve the each configuration.
Thank you for your
Okay.
answer.
All right, so thank you very much for your presentation. Let's move to the next presentation.
Okay, thank you so much.
Okay, so the third paper is Aircraft DX in Commercial Aviation Systems. And this paper is presented by Dr. Yasuhiro Yamaguchi. And he is currently a project leader of national program Aircraft DX in Commercial Aviation Systems at Mitsubishi Heavy Industries. But formerly, he has been working at Mitsubishi Aircraft Corporation, and he acted as who is responsible for the aircraft integration activities in MSJ, Mitsubishi Space Jet Program, and also the technical leader of MBSE project. Okay, so Dr. Yamaguchi, please.
Thank you, Chairman. And also thank you for giving me the opportunity to conduct this presentation. Okay, today I will explain that my company, Mitsubishi Heavy Industries, digital transformation in commercial aircraft, especially in the development and the manufacturing two phases. Okay, this page shows that the contents of my presentation, starting with the overview my company MHI, Commercial Aviation Systems, and I will touch the topic for my company's DX, digital transformation activities. And also I will explain the NEDO aircraft DX project. It's slightly explained by the Watanabe-san. It's a national funded DX activity. And also I will finish with my conclusions. Okay, this page shows that overview of MHI. We have a variety of the product, as you can see. And our headquarters is located in Tokyo, in Japan. Today, I will focus on the DX activity in commercial aircraft area. And this page shows that three main capabilities in commercial aviation. One is the OEM. It's an aircraft integration capability, which is acquired in the development of SpaceJet, Mitsubishi SpaceJet. Unfortunately, this project was terminated in 2023, but we got a lot of knowledge and experiences in this project. Next is the structure tier 1 capability, covering for example, the 787 advanced composite technology for main wing. Third one is the maintenance, repair, and operation capability for the CRJ, operated by the group company MHIRJ. Actually, MHI buy this operational capability from the Bombardier. Today, my explanation about DX focus on these two areas, OEM and structure tier 1. This page shows that our OEM capability. In the SpaceJet program, we got the capability for the whole aircraft development against the latest certification requirement. Along with this V development process, in the left side, we started the aircraft level design and going down to the implementation, including the requirement validation according to the ARP 4754 process. On the right side, it's a verification area. We conducted the integration and verification to the top level aircraft with these integrated test facilities and flight test vehicles together with the global suppliers. But in this phase or integration activity, we had a lot of troubles in mainly the integration process. So one of the most important lessons learned we had in this project is that we had to establish the mature and practical process before starting the project. And also we need to consider that the interoperability with the global suppliers to share the technical information, especially in the integration process. This lessons learned is that key driver to start the DX activity in the NEDO project. Next page shows that Tier 1 capability. We have various commercial airplane products to the world-leading aircraft manufacturers, including Boeing, Bombardier, and Airbus. Currently, these are the main products in our commercial aviation section. So we need to improve and enhance the market value of the product. This is also another key driver for our DX activity in this Tier 1 area. Okay, next I will introduce the DX activity in my company. This page shows that, current issues in commercial aircraft. This left bottom size figure, this is my favorite one, shows that only the aerospace vehicles need a longer development time due to the increased size or complexity of the systems. One of the reasons, I believe, is that aircraft has an integral architecture, which means that there is a close relationship between function and the physical architecture. Sometimes or always, this kind of the architecture need a more negotiation or integrated analysis in the design process. And as a result, in most cases, we need to conduct design changes in the later integration phase of the development. That is one of the reasons for this issue, I think, or main issue, I think. And another aspect is that the more workload by process assurance against the type certification, as I mentioned for the ARP 4754 process. And also, another aspect is that paper document manual tasks still survive due to the long life cycle of product. For this Boeing, for example, this Boeing product, the production or development start in the 1980 or something. In this project, we still have a lot of paperwork process due to its long life cycle. Of course, as already mentioned, we need to continue the improvement for the QCD, quality, cost, and delivery in each project. So, to resolve this situation, we need a solution by utilizing the digital transformation. Okay, this figure, this page shows that explain that the two major DX activities ongoing in my company. One is a DX for future commercial airplane development. It's a national aircraft DX project funded by NEDO to prepare for the next aircraft development. It covered that design, certification, and the beginning of the production phase. Another DX is a Tier 1 DX, Tier 1 area. It's a company internal activity covering the production and later. In the following pages, I will explain that Tier 1 production DX activity first. After that, I will explain that more for this future DX activities. Okay, as I mentioned, this is a bottom-up approach for customer satisfaction in ongoing programs like Boeing 777. And we need to conduct this DX activity while keeping the stable production. We cannot stop this kind of manufacturing. I will pick up 3 typical examples in this activity. Case 1 is a DX in integrated supply chain. Data from all the global suppliers are collected, and we established that a communication tool to store that information and shared with the OEM. It means, for example, Boeing. This collected data is analyzed and visualized as integrated supply chain data with the Boeing, for example, and supporting the total stable production to check any issues as quickly. Second example is that high quality. We use the smart glass to project the various supporting information as augmented reality to improve the workers' cognitives. This figure shows that image of the smart glass through the smart glass. These colored circles or triangles and rectangles indicate that the part should be installed in this point. Also, worker can check the work instruction with portable PC. This kind of DX will reduce the human error and lead to the more high quality of our production. Third example is the digital traceability. From the material purchase, beginning of the supply chain to the delivery, various production data in supply chain is collected and linked. Database system to provide the quality record to OEMs. In case of some trouble happens in OEM, we can assess that impact on the manufacturing line by seeing that all the required information. I will pick up the 3 examples in DX activities, but as I mentioned, this is a continuous improvement process, and we are doing a lot of more other activities. And we will continue that kind of activity through the next aircraft development. Next section, I will explain that the NEDO aircraft DX project. This is an overview of the NEDO aircraft DX project already mentioned by the JAXA Watanabe-san. The objective is that innovation and process integration in aircraft design, certification, and production. And this figure shows the image of the this DX activity. DX platform, which can be used by the Japanese manufacturer for the commercial airplane, can use this DX platform. And on the platform, tools for design DX, certification DX, production DX will be installed. Project was integrated by JAXA, and we, MHI, is one of the key persons in the project. And it's a 5 years project starting from the 2023 to the 2027. And this page shows that the overview of our company's DX activity in the project. We are participating in the design DX, production DX and certification DX activity. In the design DX, starting from the top stakeholder requirement, going down to the subsystem requirement, preparing this system model described by the system language. And the data was linked each other. And also we will make a linkage with the analysis tool to realize a more automated design process. And the bottom of the design DX is the interface with the production DX. In the manufacturing point of view, this 3D CATIA model is the most important information. And we plan to make a linkage between this CATIA model and system model. And it will realize a total data linkage from the design to the production. And we believe that this kind of the data linkage will minimize the negative impact on the production line in case of some top-level requirement changes in the project, because we can easily assess the impact on the productions. And certification DX is a top-level verification activity against the regulations. And we have two key features. One is that we will prepare that model for the compliance. We will use this model for the negotiation with the authorities, certification negotiation with the authorities. And we will prepare the compliance metrics with the system model in the certification plan. Another key feature is the CBA, certification by analysis, to replace some physical tests with analysis. And also in the future, we plan to prepare the set of the analysis tool covering the design and also the certification. And as you can see, that the SysML MBSE is that one of the key methodology to integrate all these three DX activities. I will explain a little bit more in the following slides. In the design DX, we are developing the design process utilizing the linkage between the system model and analysis tool like a CFD, and realize more automated workflow in this. The pass or fail against the design requirement is automatically judged for multiple design candidates. And also, this tool can support the set-based design approach, which enables us to deal with the multiple design candidates through the development phase. This is the overview of design DX. And this page shows that overview of certification DX, especially in the CBA, certification by analysis. We are exploring three domains: flight characteristics, structure, and lightning, to replace some TC tests with analysis. Our Mitsubishi SpaceJet test data is used for the verification and validation of analysis tool, also covering that uncertainty quantification. This is one of the key process for CBA activity. And another feature is that we plan to conduct a trial audit with Japanese authorities using the system model compliance metrics. And at the end of the project, we will publish the CBA guideline covering the process and the lessons learned. Okay, I will explain for the production DX. As I mentioned, from the manufacturing point of view, 3D CATIA data is the most important. So we believe that in the V process, we need to conduct a parallel activity. One is for the system model, MBSE, and other is that geometric model for 3D model. I think these two activities should be synchronized in the design process, development process. And another thing I want to mention is that this is a product aircraft V process. We need to consider that the production system V process. also covering the system model and also the 3D model for production system, and make a data linkage between these two V's. It will enable that we can start the production system design at early stage of the development by using the information from this system model. Also, we may be able to change the aircraft design by considering that the limitation of the production system or some requirement for the production. This kind of the linkage will also reduce the risk of the design changes in the later phase of the program. And from these 2V process information, we also plan to prepare that these data required for the manufacturing preparation. From these two processes, we will prepare that, for example, the E-bomb, it's a bill of material. Also, the BOP is a bill of process. It's a kind of the manufacturing process development, and the work procedures and instruction with augmented reality. This kind of the information can be prepared based on these V process information, also linked each other in this one PLM, Product Lifecycle Management Platform. As a result, for example, that worker can access to the necessary information in single source database. This kind of the situation, I think that we can drastically reduce that manual task in manufacturing preparation. And also we can reduce the risk of a human error in this process. This figure is a kind of the final image of the production DX activities. Okay, so finally the conclusion page. As I mentioned in the introduction in my presentation, we need a strategic plan to apply DX in commercial aviation due to its long-term life cycle. And also, we need to consider the interoperability with the worldwide suppliers, stakeholders. And also, we need to consider the complexity of the systems. In the future, as a future plan, we want to integrate two DX activities from top-down approach and bottom-up approach in the next aircraft development. Also, we want to get the synergy effect with other MHI, our product in the future, like a defense, fighter or tank, and space vehicle, ships, plant, and so on. One of the important things is that the standardized tool process development to improve the total company level QCD. Also, DX platform development is important to make a collaboration with the Japanese companies. That's all for my presentation. Thank you for your attention.
Thank you very much for your presentation, Dr. Yamaguchi. Okay, so the question time. Yes, please.
Hello again. Thank you for the presentation. But by the end of the presentation, you mentioned that digital transformation could be a way to reduce human error in the assembly plants and so on, and also decrease costs and improve quality. Could this also be a way to reduce, waste components in the design of the airframes and the design of the aircraft parts?
Yes, thank you for your question and comment. Yes, I totally agree with you that I emphasize that, how can I say, merit for the company, but also that green innovation point of view, DX is mandatory to trace all the consumption, energy consumption, and waste of the materials. So of course we try to utilize this once establish the DX process to improve that such a kind of the green transformation.
Hello, thank you for your presentation. Alex Sixton from the Aerospace Technology Institute in the UK. I had two questions. One was, there are obviously a lot of aerospace companies that are looking at the benefits of digital transformation and looking at similar methods and tools. So my first question is, did you consider collaborating with other aerospace companies, software providers, to provide you a solution that wasn't unique to you but might be something that provided the benefits or requirements of other organizations? My second question, I guess, follows from that is, when do you see your earliest implementation of some of the things you've been working on? Because some organizations are maybe waiting until the launch of a new platform. Some organizations might be putting it in sooner.
Sorry, I think I understand the first question, and my answer for the first question is that I think there is two domains for the collaborative area and also the company IP areas. So we need to clarify these two areas. And for the collaborative area, I think we can or we need to make a collaboration with other aerospace companies, because that the investment for the DX is very huge. So each company cannot have such a enough money or budget for that to realize a total DX view. So the second question, could you repeat again? Or
Was the implementation sort of time frame? When might you see some of the benefits of the methods that you've been developing?
When, the timing? Okay, so as I mentioned, for the Tier 1 DX activity is ongoing, so already it's implemented. And brand new DX project for NATO project, that, as I mentioned, that research program will continue for 4 years. And at the end of the project, DX platform will be established. But my question for me is that when we can utilize this DX platform for the new aircraft development, this is depending on the market or the other major OEMs activity. But anyway, our plan is that in these 5 years, we need to establish these kind of the DX tool and procedures. Am I answering to your question?
Yes, thank you.
Okay. So any other question? So I have one question.
Yes.
And at the beginning, you mentioned about lessons learned, and one of which is to establish the potential and mature process.
Yes. Mature and practical process.
Practical, yes. And so throughout this DX project, do you think your target will be achieved or not? Or
yes,
still there is a lot of...
I believe so. I believe so. This is that, of course, DX activities, and it's a more, how can I say, upgraded practical and efficient process we can get at the end of this project, I think. In the SpaceJet program, we need to conduct a parallel, how can I say, some modification of the process will be required after starting the project. That caused a lot of design changes and confusions. But after this DX project completed, I think that we can improve the situation and we can get, how can I say, powerful tool to start the aircraft development.
Okay, thank you very much. All right, so if there is no other question, I would like to move to final presentation. Okay, thank you very much, Yamaguchi. So the final paper is, we will go back to the sustainability topic. development of aircraft system electrification and hybrid electric propulsion. And the paper is presented by Naoki Seki, and he is now engaging in research, development, design, and MRO business of aircraft engines at IHI Corporation. And also, he has been engaged in the research and development projects of aircraft electrification by the Japanese governmental funding. Okay, so Seki, please.
Thank you for your kind introductions. And today, I'd like to present the development of aircraft system electrification and hybrid electric propulsions in the Japanese activities. So at first, it's the same way, but you may not know about the Japanese companies, so I would like to introduce myself and my company's introductions. IHI is established in 1853. Last year, 170 years celebration we did. And we started at first shipbuilding. Shipyard was our first jobs. And right now, we have 4 business areas. One is aerospace, but the other was the energy solutions and the social infrastructures and the general industrial systems. And so when our company is considering about the aircraft systems electrification, we are thinking about the collaboration, internal collaboration for the new aircraft systems. And so IHI is one of the largest aircraft engine manufacturer in Japan. And we are considering towards the carbon neutral society, including the aircraft electrification, and also we are traditionally in this 20 and 30 years, we are doing the composite material implementations for the aircraft systems. And right now, we are doing the electrification systems development. So from this chart, you've already shown about this information, but right now, we agreed, we committed for the carbon net zero at 2050. And as you know, not only the technology, but also the alternative fuels and operation improvement are important. And in the technologies improvement, electrification is one of the pillars. But also there is a more efficient technologies and lightweight and aerodynamics improvement will also be required. And my company is now tackling for the electrification and also the lightweight or more efficient technologies to implement the FRP composite material technology to the aircraft engine and also the fuselage. So from this chart, so I would like to introduce what IHI is now developing for the aircraft system electrification. So when we talking about the aircraft system electrification, so many of people are talking about the hybrid electric propulsion. So yeah, that is very easy to understand. but we consider still the aircraft systems electrification is not finished. It's ongoing, and this is a large part of the systems electrification. And also we consider the integration between the aircraft system and propulsion is very important. So if you only put the battery, if you only put the large generator to the propulsion systems, the weight penalty is so huge. So we should need the systems integrations and the optimization, integration of the system is mandatory. So to achieve that, we are doing the several key technology development. So we've started the more electric aircraft systems development at first. So one is the ACS, that is a very high capable air cooling system for the power electronics. That means the motor controller or converter, such kind of the systems. Now we need the liquid cooling systems, but we enlarge the capability of air cooling system and integrate to the air management system of the aircraft system. And the other part is the rare. Rare is a laminar heat exchanger abolished ECS system. So this is this consists of the two concepts. That is a fuel cooling ECS system, and also the energy recovery with the electric turbochargers. So IHI is one of the largest turbochargers supplier in the automobile industries. And based on that experience, we are developing the electric turbochargers that can be used for the aircraft systems. So to implement this kind of technologies, so with this air cooling system, we gather all of the wasted heat from entire aircraft to the turbochargers turbines, and to recover the energy from the cabin wasted air. And also the MIFI, that is a electrified fuel control system. So that use the hyper-density motors and fuel metering with the pump speed control. So that can eliminate the fuel recirculation by the valve controls in the typical fuel control system. So it will enlarge the thermal management capability of the engine. And we integrate the aircraft systems, thermal management system, and engine thermal management system through the fuel, burn flow fuel. And for the hybrid electric propulsion, IHI is developing E3M. E3M means the engine embedded electric machine, and that is a megawatt class generators. So that can be direct mount on the AP spool. This generator is capable with the environmental temperature in the telecom. So very high heat resistant generators, and megawatt class output we've already tested. And one more is the air supply system for the onboard fuel cell systems. So that is also the technology is coming from the automobile turbochargers. So IHI is already provided product for the automobile industries, this kind of technology. air supply system of the turbocharging unit. And similar technologies is using for the aircraft onboard fuel cell system. So I've introduced the key element of the systems, but this kind of common key technologies can be used for the wide range of applications. So the key technology is the consists of two types of the technologies. One is the high heat resistant motors that included the E3M and MEFI. And the other is a gas bearing ultra high speed motor. So that can be used for the turbochargers. And these two technologies can be used for the, for example, in the regional class aircraft, it can be used for the FC propulsions with the FC fuel cell systems, air supply unit, and also the propulsion unit. And for the singular class or much larger class aircraft, that can be used for the hybrid electric propulsion systems. And we are considering to use the fuel cell system to the APUs. That can be also used for the all sides of the aircraft. And also one of the important pillars is the thermal management. So if you want to use the large electricity in the aircraft, so that is a closed areas. So, and that is very difficult to dissipate the heat. Megawatt class generators and the motor controllers dissipate so much heat. But typically, such kind of the heat coming from the fuselage is very difficult to dissipate. But our concept is to gather all of the wasted heat through the air and combine with the air and thermal management system, and again combine the aircraft thermal management and the engine thermal management. This kind of the integration works IHI is now trying. So next chart. So this is what we did in the past national project. So we've already did 2 national projects, and we are now doing the third project. And the first project was done in the 2016 to 2019. In that project, we did the subscale demonstrations for the 250 kilowatt class, first generation E3M, engine embedded electric machine, and also the first generation of the electric blowers, ultra high speed blowers. So in this project, so 250 kilowatt class E3M with hyper density and heat resistance was demonstrated. And air cooling system for the 100 kilowatt class power electronics was demonstrated. So this project was funded through NEDO, so New Energy and Technology Development Organizations, so subsidiary of the METI, Ministry of Economy and Trade and Industries. The second project was done from 2020 to 2023. So this is a Japanese fiscal year and ended by the March. So just a half year ago, we've finished this project. And this second national project, we did the full-scale generators demonstration and partial system demonstration we did. And in this project, we've manufactured and tested the 1 megawatt class E3M and 70 kilowatt class ETC, electric turbochargers. So 70 kilowatt class electric turbochargers can be used for the fuel cells that can cover around the 700 kilowatt output fuel cells. So for example, if you need the 2 megawatt class fuel cell systems, well, we can provide 3 these ETCs for the air supply system. And so we've developed this component, but still the system levels testing is partially done. That is mainly coming from the restriction of the testing facilities capabilities. And so the third project has started from the GI funding project. So this is a green innovation funding coming from the METI. We are now doing this project to do the full-scale system demonstration for this, for example, the megawatt class generators with the electric power distribution system, and also the 70 kilowatt class ETCs with the fuel cell air supply system for full scale, and also the aircraft environmental control system with this electric turbochargers. So this chart and next chart shows the what we are planning in the GI funding project for the aircraft electrification. So the title of the project is the Electric Power and Thermal Air Management System and Equipment Electrification. So this title shows that, yeah, everything electrified. So we are now trying. So to achieve the TR6 for the core technologies in the electric power and thermal air management system by 2030. That is the objectives of this project. And in this project, the target of the fuel efficiencies improvement is 5% or more compared to the current single-aisle aircraft, and demonstrate its feasibility under the operation conditions. And in this project, 2 core technologies has already mentioned, and one is the 1 megawatt class generator with a power density more than twice of that conventional aircraft. And electric turbo compressors, turbochargers with the world's largest output. Currently, 55 kilowatt is the largest, and or more for the aircraft use. And to create environment where the core technology can be adapted, so participate in the standardization activities. So that is one of the pillars in this activity. And here is the again the concept of the aircraft, and this is one of the examples when we implement our system to the aircraft. And for example, the hybrid propulsion systems with the 1 megawatt generators, and also the engine will need the HP starter generators. So we are considering the power extraction and injection through the generators from LP spool to HP spool, or HP spool to LP spool. And also the environmental control systems. So that is the thermal and air management systems, the part of the thermal and air management systems. We are now planning to demonstrate entire ECS system with the air cooling systems and the concept of the gathering the wasted heat to recover the energy. This kind of concept proof testing will be done in this project. Sorry. So this chart and next chart shows the key technology development. The first one is a megawatt class engine embedded electric machine, A3M we call. And we've already developed the megawatt class E3M in the previous project. But we are now trying to make the next generations. So currently, not all of the tests for the, especially for the environmental compatibilities is not tested yet. So we will done that, and also the system levels. So electrical distribution systems levels test will be done in the next project. And the other is the high power output electric turbo compressors. So that can be used, again, that can be used for the air supply system of the fuel cell, and also the ECS systems. We are now design and manufacturing this ECS, ETCs, and we will do the system testing. And one of the important things is the ground testing facility is one of the key points. And for the preparation of the ground testing facilities, we are collaboratively working with the Akita University. This is outside of the current need of project, but to using this kind of collaborative activities, we are preparing the actual megawatt class testing facility, and also the entire aircraft system levels, air systems testing facility, we are now preparing. And this one is the last chart, but we also doing the activities for the standardization. So traditionally, Japanese company is very weak presence in these areas. So we are trying to make our presence much bigger in the international standardization activities. So the conclusion. So aviation industry committed to the aggressive goal, net zero 2050, and all technology options should be pursued to achieve it. IHI will contribute to the net zero aviation through the electrification technologies by bringing our wisdom all together from not only aero engines business area, but also others in IHI group. And our final goal is to provide safe, comfortable, economical, and eco-friendly air transportation system. And the acknowledgement. So this presentation is based on the NEDO project result. Yeah, thank you for listening.
Thank you very much. So any questions or comments from the audience? First.
Oh, sorry. Thank you for the interesting presentation. I've seen some components you develop which may suit as a replacement for existing components, but other components are more useful for embedding in a larger system. So I just wonder what your plan is regarding cooperation and embedding the systems with OEMs, because I think it's not only for your own products, as you explained, but maybe for other OEMs like Airbus or Boeing or other aircraft companies. So when do they come in? This is basically the question. Are they already involved, or do you develop these technologies and then if it's mature, you propose it to the companies to be included in future products?
So IHI has started the electrification development around 2011, so 13 years ago. And at the start point of that project, we had a discussion with the OEMs. So this type of the technologies, the orientation of the technology development is always aligned with the OEMs. So that is the answer.
Thanks.
Okay, so.
Thank you for the presentation. I have a question. I'm very interested in your presentation about the electrical motor. I have a question. Do you have any plan to finish your research and development and then apply it to the aircraft?
So of course we are proposing to implement our motor for the actual aircraft. So for example, the testing is already planning. So we are planning with the JAXA to implement this kind of motor in the actual aircraft engines, but it's a kind of the testing, and your question is the actual implementation for the product.
Thank you. So I have another question. So if the electrical motor is more than 1 megawatt, I think the thermal management is quite important. It's very complex. What method or what system will you use in your electrical motor?
So for the electrical motors, we are considering one of the key points is the high heat resistant. That is the two meanings. One is in the aircraft systems, so the voltage is typically very limited comparing to the ground-based systems, and the higher current will cause very high heat dissipations. That is one point. And the other is IHI is the engine manufacturers, and when we consider the engine integrations, so normal operation temperature is only around 200 degrees Celsius. That means the oil can reach such kind of the temperatures. But in some cases, you should think about the more harsh environment. So for example, the cooling less, such kind of conditions, we should withstand some time durations. So to considering about such kind of conditions, we determined that the high heat resistant is the most important key part if we integrate the electric machines into the engine.
Thank you.
Okay, so If there is no question, no? Oh, all right, okay. Thank you very much for your presentation.
Thank
you. And now, I would like to close this special session. Thank you very much for your cooperation. Thank you.